Hello, my presentation today focuses on termite mounds, inspired ventilation and thermoregulation, and how it can be applied to urban towers. These natural strategies offer solutions to reduce energy consumption and improve sustainability. First off, what's biomimicry? Biomimicry is a practice of learning from nature to solve human challenges. In architecture, this means observing organisms and ecosystems that have evolved over millions of years. Termite mounds provide an extraordinary example of natural engineering. They maintain consistent internal climates in harsh external conditions using passive strategies that do not rely on mechanical systems. By understanding these natural principles, architects can design buildings that are more energy efficient and sustainable. So what's the challenge? The challenge is urban towers, which often consume enormous amounts of energy, specifically for heating, cooling, and ventilation. These large buildings are highly dependent on artificial climate control systems, which increase their operational cost and environmental impact. This is particularly problematic in hot and environments where cooling systems work overtime. Traditional solutions include conditioning and mechanical ventilation, both of which use a lot of energy, which in contrast, by mimicking natural ventilation and thermoregulation strategies found in termite mounds, we can easily and drastically reduce the energy footprint of these towers. Thermoregulations in termite mounds. So, termite mounds maintain stable temperatures and airflows despite fluctuating external conditions. During the day, the thick earthen walls of the mound absorb heat. At night, the heat is slowly released, preventing extreme temperature fluctuations inside. Internally, termite mounds have an intricate network of ventilation tunnels that allow air to circulate naturally. The cooler air enters the lower parts of the mound, while the warmer air is expelled through the higher tunnels. This passive ventilation system regulates both temperature and humidity without mechanical input. In architecture, we can replicate this through thermal mass materials, such as stone or concrete, which store and release heat. Additionally, the design of ventilation shafts can mimic termite mounds, channeling airflow to regulate internal climate without the need of extensive HVAC systems. As shown in the graph, we see that the arrows pointing down are mimicking or are projecting the cool air entering the lower shafts, and then the hot air, is expelled through the top tunnels. This is the system that termite mounds use in order to keep the environment cooler or warmer in the inside, alongside the porosity of the material. So what's the case study? The case study is the Eastgate Center. The Eastgate Center in Zimbabwe is a modern example of termite mound inspired architecture. The building relies on passive ventilation and thermal mass to cool and ventilate itself. Like termite mounds, it uses thick walls to store and release heat, and it has the intricate ventilation system that allows air to circulate naturally. This design reduces the need for artificial climate control, cutting energy consumption by 90% compared to the conventional buildings. The success of the Eastgate Center proves that biomimicry is not only feasible but also highly effective in real-world architectural applications. So I have developed a flowchart that explains the termite mounds and their use in architecture alongside other terms that directly connect to termite mounds, like also some more concepts that connect to this biomimicry concept. So the flowchart shown here breaks down the various strategies inspired by termite mounds, from gaining heat and airflow to dissipating excess heat and preventing overheating. This chart demonstrates the connections between biological processes and their architectural applications. So the functions, for example, the primary function of termite mounds is to regulate heat, maintain airflow. Then we move on to processes. To achieve this, they absorb solar heat during the day and release it at night, while circulating air through natural ventilation. Then we move on to the factors. The key factors include the surface porosity of the mound, the material conductance, and the airflow efficiency. Then we move on to the pinnacles and the applications. So in the pinnacles, we found that nature's inspirations, such as termite mounds, influence how we build urban towers using porous walls and ventilation shafts. Then the applications in buildings, these principles translate into high thermal mass walls, natural ventilation channels, and moisture control systems for evaporating cooling. So for the Python coding, I developed a game that basically guides the user through picking passive strategies, to picking the building type, picking the weather zone, and then it starts to give feedback according to the user selections. And this feedback will determine how efficient the building will be throughout 100 years of the living span of the building. So I will show this at the end, which is how the coding works, but we'll keep going with the presentation. In conclusion, biome- uh, biomimet, uh, biomimetic design, specifically inspired by Termite mounds, provides sustainable, energy-efficient solutions for modern architecture. By applying principles such as passive thermoregulation, natural ventilation, and moisture control, we can drastically reduce the energy footprint of urban towers. Looking ahead, these designs will play an essential role in creating greener cities, especially as the demand of eco-friendly, resilient architecture grows. The future of urban towers is not mechanical systems, but in learning from nature's own designs. Again, explaining a little bit more about the Python simulation of termite mound strategies is to better understand the long-term effects of termite mound inspired strategies. The simulation that I developed, in this one, the user selects different passive cooling strategies such as high thermal mass, ventilation shafts, and moisture control, and the program calculates how these choices affect the building's efficiency over time. Over the span of 100 years, the program demonstrates how passive strategies can significantly reduce the consumption. So I'll be sharing now the citations, and I'll be sharing now the code that I have developed. Here we go. So in the code, what I basically did is that I set all the variables, all the strategies. So thermal mount walls, high thermal mass, ventilation shafts, ribbed facades, then the climates according to the Köppen climate zones, the tropical rainforest, arid desert, etc. Then the building types, whether it's a house, a skyscraper, a tall building, or a mixed use. I gave them all coefficients. These coefficients are were researched. Which I have all the citations and all the research, which is going to be attached to the video. The shapes, um, which come from previous classes in the architecture school, and then basically all the code, which is asking the user to select either or from each one of the prompts, and then the calculation of the of how efficient these strategies are for um, each unique scenario. So when I click run here, it is going to ask me the select Köppen climate zone for your building. So say I want to do Savannah. Then it's going to ask me the type of building that I'm going to be using. I will be selecting house. Select the building shape. I will be selecting rectangular. Then then it's going to tell me the shape factor, which is 0.95. It is always going to be reminding me of the factors, the coefficients, and the numbers that are going to be ultimately affecting the final graph. Then it's going to tell me enter the building area, say 350 square meters. Then the number of stories, say this is a two-story house, and the orientation according to the north to see which side of the house is receiving more sun. So say it's 45 degrees. This only means that the north is going to always be the point zero reference. So if I'm going 45, I'm slightly turning this way, counterclockwise, because when you have positive degrees, you turn counterclockwise. So you turn 45 degrees. Then you select the passive strategies. Say in this one, I want to select the one I researched. So termite mounts walls. Say I want A. Then it's going to ask if you want any more. I will say no to this, and I will make this my final decision. Then it is going to plot a chart that is going to show you the which is here, that is going to show you the efficiency of the building throughout 100 years. So the building, percentage-wise, is going to be 50% efficient, uh, which means that it's not using all the capabilities that we could be using for this specific building, which now we can go back, reiterate, and see which strategies will be better for this specific building. Then let me show you the research which I have here, where I compile all the information that we have talked about so far. This is my research on the termite mounds. I first develop on the termite mounds. I go deep into understanding the shape, the airflow, the porosity, the materiality, the size of the holes, how it creates negative pressures, positive pressures, high pressures, low pressures, and then how it starts to also control the humidity and all the environmental factors that the termite mounds have into considerations, then how to apply them into architecture as chimney structures, lower air inlets, and internal tunnels, which is also shown in the case study. Then diagrams to show the process and the applications in architecture. So addressing the environmental factors, uh, talking about the specific case study, which is the Eastgate Center by Mike Pierce, how this building created the high pressures at the bottom to push and release the hot air at the top through the chimneys, the picture of the project in Zimbabwe, and then the factors affecting the application of termite mounts, the principles in urban towers, and then other case studies that utilize these factors, pictures of the case studies, and I have all my bibliography here, and that's about it. Thank you.